Okay, sound testing. All right, good. I am again, as usual, I'm having trouble connecting to my secondary screen, to the one that I use for drawing. And and of course, I'm gonna need that one to make some sketches today. Well, I don't know. I'll get that. I'll get that ready. Good afternoon. How's everyone doing? Are you ready for more geometry goodness? All right. Are we doing this? Where are we doing this afternoon? I'm going to do a very quick exercise. It's going to be a simple geometry gem. It's going to be finding. So you know how we can have a point in three-dimensional space in world coordinates, right? But if we have a plane somewhere, if we have a local coordinate system, how can we find the coordinates of that point from world coordinates into the local coordinate system? Oops. So we're going to do that today. Then we're also going to learn how to change from one local coordinate system to another local coordinate system. So a process that is called a change of basis. And we're going to use that to learn what to do the geometry gem that was suggested this morning, which was, what was it? It was finding the bounding box of a cloud of points. And I just realized I wasn't recording, so now I'm recording, at least locally on my system. Okay, but all of this, if I can actually get my drawing board ready, which is not connecting right now, of course, because I don't know what's going on today, but things are just not working well. How's everyone doing down there? BVR, Monique, Dusko, Andres, good afternoon. How's everyone doing? I am going to, I'm going to start setting things up here. Okay, I'm going to set up my rhino and my grasshopper here. Okay, and so I got that set up and I got some notes here. And hopefully I will be able to get my drawing board working somehow. This computer is not, I don't know what's wrong with this computer. Anyway, how are you spending your weekend today? Are you doing anything exciting tomorrow? Okay. Okay, so we got that. That looks like it's working right now. And I'm going to start a new file here. And I'm going to drop some bifocals because, of course, people that don't like icons also deserve some attention. My computer is definitely being spooky. It's not very happy today. Oh, it was blocked before. That's why. Okay, and what if I try to connect now? Yes, I got it. Woohoo! Okay, did you see that flash? That was a good sign. And which means that I can bring this here. I can fold my drawing thingy on. I can start a sketchbook here. I can bring my layers all the way here. Correct. And if I do this, I should be able to draw stuff. Is that correct? Like P camp. Woohoo! Wait. Where am I? Yeah. What? And look. Okay. Sorry, I had to do that. All right. I think after this, maybe we're ready to start, or maybe we're just not ready to start at all, ever. All right. Yes, Rafael, I also worry about the election. I worry about many things. The world is a little complicated these days, but hopefully things will get better, one way or the other. Okay. So, let me get started. How are we going to get started? So we're going to start. Yes, we're going to start. Let me draw some sketches here. Okay, so we're going to start with a gem. That is, we have a point in world coordinates. How do we find what those coordinates are in a local coordinate system defined by its center and 3 axes, right? So let's start by doing this. Okay, so that is global coordinate system. X, this is going to be, no, this is going to be Y, okay, and this is going to be C, okay, alrighty, and then next layer is going to be, we have a point here. That is a terrible point. Why am I not, what's going on with this? Okay, so let's have a point here. This point is going to be a thick dot. So what we're going to do now is we're going to draw here coordinates, right? And then here and here. Okay, so those are the XYZ coordinates, I guess. But now what we want is we want to say, well, maybe, okay, so maybe somehow I have here a different coordinate system. How am I going to draw this? Oops. How am I going to draw this so that it makes sense? Maybe I have another coordinate system here, for example, and then here, and then maybe here. And then now what we want to know is what are the coordinates of that point in this other, right? In this other coordinate system, right? And actually, wait, so maybe we can draw those maybe we can draw those differently. What if we draw them like this? What if we draw them, this is the x coordinate, right? This is the y coordinates. And what are the z coordinates in that coordinate space? That was a terrible drawing, huh? I'm only getting worse at this. Okay. Yes, so maybe this is here, maybe this is here, and maybe this is, I don't know, here. I guess that's just not right, doesn't feel right. And also all those points, I think I did not do a good job there. I think it should be more like this, right? It's very difficult to write on this thing, actually. Okay, so, and then, because those I want to join here, and those, kind of. Okay. All right, so what I want is if this point has some x, y, and C coordinates. Sorry. I'm actually going to write here X. No, so this is going to, X is going to be this one, right? X is going to be this one. Y is going to be this one, and C is going to be this one. What I, yes, so this is going to be X, this is going to be Y. Let's do colors for that one. If this is going to be the value of X, all right, this is going to be the value of Y, and then this is going to be the value of C. Okay, so if that's what we want, then probably when we do this, we also want to find what is the value of small c, okay? What is the value of small x, and what is the value of small y? Okay. This doesn't look that terrible, does it? Okay. And then for the next gem, what I can do is I can just draw somewhere here. I can just draw somewhere here another plane, and then I can do like, now I want to find what the new point, what the coordinates are in that. Okay. All right. Actually, I don't really like this diagram that much because since I'm going to be doing projection of vector projection, since I'm going to be doing vector projection, it's not very intuitive actually. Oh God. All right. So, okay, so this one is going off. And what I want is, so what are the coordinates? What are the coordinates in this direction? Okay. So what is the coordinate in this direction? And what is the coordinate on this direction? This is just not. Okay, so if I have this and I have this, okay, and I have this and I have this. All right. Now, what I want is another layer where I can, what I can say, well, now, what is the projection in the x direction? It's this one. What is the projection in the y direction? Is this one. And what is the projection in the c direction? It's going to be this one here. And I want, you know, that, and then that here. Okay, I'm a little happier with this now. So therefore, this would become small x. Nope. This would become small x. This will become small y. And this would become small c. Okay. Yes. And then here, where do I have those letters? Okay. This one I'm just going to not. Okay. Can I delete this? How do I delete? Yeah, delete. How do I delete this one? Delete. Yeah, this one I also don't want it. And so I guess here I need to add another layer, and I basically want to say here I want to have, and this is the big coordinate of x, Here I want to have coordinate y. Here I want to have coordinate z. And then these are going to be the c value, this is going to be the y value, and this is going to be the x value in world coordinates. Okay, I think I'm finally somehow happy with this. So yes, so the story we're going to tell is we have a world coordinate system, we have a point, and then that point we want to find out, oh, what? Oh, here. So this needs to go here. So the story we want to tell is like, okay, what are the coordinates of this point in world coordinates? So it's very easy. We project, and then we find what those projections are, and those become the value of x, y, z. All right. But what if we have a local coordinate system somewhere in space, for example? So what we do is we can also project to those coordinates, and then we can find what the local coordinates of that vector, of that point in that coordinate system are. And this is what we're going to do today. Okay, I'm semi-satisfied. Thanks for your patience. So let's get to this now. Okay. And we have a point. And there you go. Okay. All right, so I'm going to start, I will do the introduction later, and then I'm going to start by explaining the problem, and then we're going to go back to coding. Okay. All right. Okay. Am I ready for this? Is everyone ready for this? Okay. Let's do this then. Okay, let's start by the beginning and let's start describing the actual problem that we're trying to tackle with this gem. The idea is that when we work with three-dimensional geometry, and we're going to work with the simplest kind in this exercise, which is a point in three-dimensional space, we have some sort of global coordinate system that we typically refer to as the world, which is the base of the coordinate system that we use to define every geometry that we have in our environment, right? So for example, this point may have whatever x, y, z coordinates in the world coordinates. And typically what we do is that we measure, what we do is like to know what the actual x, y, z coordinates in world coordinates are, what we do is we measure in each direction how far off that point is in units, in the whatever units we're using, and we measure that length along each one of the x, the y, and the z axis, and then what we get is the value for its x coordinates, its y coordinates, and the z coordinates. That's typically what we work, how we work in world coordinates, and it's something that we are very used to and we actually kind of get for granted right now, right? Okay. However, what the problem that I want to describe here is slightly different, because very often, depending on what we're doing, we may actually have local coordinate systems or other coordinate systems that are not the world, and that we, for some reason, we want to refer things to. This is very common, for example, in robotics, or this is very common when we're modeling in Rhino and we choose like a different C-plane to be working on, right? That's basically what we're doing, is we're defining local coordinate systems that are somewhere else, and we want our numbers and our coordinates to refer to that coordinate system. So let's imagine we have a coordinate system in somewhere in the world, and the way to define this coordinate system will probably be something like defining where the center, the origin of that local coordinate system is, and which direction the three main axes, x, y, z, for that local coordinate system are. All right? If that's the case, then I may actually want to find this point which has global XYZ coordinates, what are the actual coordinates of that point in reference to that local coordinate system that we're working with. So in this drawing that I have, like very qualitatively, I could see that the XYZ coordinates of the point in world coordinates are probably going to be very large because it's fairly away from the center. But in these local coordinate systems are going to be much smaller number because it looks like the coordinate system that is very close to the point, right? Now, how would I actually find those values? Well, we would actually do the same operation that we do mentally when we work in world coordinates. We would pretty much do it with this local coordinate system. What we would do is something like, we would figure out in the direction of the main three vectors of that coordinate system, we will find out how far along each one of those directions this point is, and then measuring each one of those directions, we would get the XYZ coordinates of that point in that local coordinate system. All right. So this point will basically have two sets of coordinate systems. One is two sets of coordinates. One is the coordinates measured in world coordinates, and the other one would be the coordinates measured in this other reference or local coordinate system that we're trying to describe, right? But how do we actually do this operation? Well, it turns out that that we can take advantage of a very nice property of points, which is of vectors, which is the fact that that we can. Okay, I'm messing here. Okay, we're going to rewind. We're going to rewind because I'm really messing it up. What do I want to do? Okay, I think I may need to draw another diagram for this one. I'm gonna have to draw another diagram for this one. Yes. So I'm going to have to draw another diagram for this one. Okay, so let's draw another diagram. All right. So I'm going to save this. I'm going to create another one. And what am I going to do? I'm going to say, well, this is here, this is here, and this is here. Okay. And my point is going to be somewhere here. And let's assume that the point is, let's assume that the point is somewhere here, for example. And let's assume that that point is somewhere like this. Okay. So now what we can do is we can create a vector. Okay, I really want to draw things that are a bit where are the brush options? Oops. Okay. All right. So I want. Okay. So now, let's say that. Okay. We have this. We can create this vector here. And if we do that, then basically what we can do is we can project that vector on top of here to find its projecting length, and therefore this would become local x. All right, we could project this onto this other vector, and that would become small y, and we could just project that all the way here, and then that would become our small c. And for that we can use the dot product. Do I have anywhere? Did I do a? We did a gem on the dot product. Is that correct? Point-to-point distance, game. Remove duplicate point sorting. Have we done anything with the dot product and the projection of two vectors? I'm not sure about that. Dot product. Okay. No. Okay. Okay. Vector projection. Okay. I think. Okay. All right. And so what we can do here is that I can draw a second diagram here, and I can say, and in that diagram I can draw that for any vector, and I don't want to draw this on top of my head, so I'm just going to draw it here, and I can draw that for any vector. Actually, I think this is okay. So turns out that for any vector like this, and for any other vector like that, like this projection, this length, the projector and vector v, and it turns out that L is equal, the length of the projection is equal to the dot product of A times B divided by the length of vector B. And if this B is a unit vector, then this is just equal to the length. Okay. It would be bigger for the dashed line brush to be a bit bigger in size, the gray ones. I know, because the lower card, they cannot be seen at all. I know. It's just that it's a pain in the ass to now redraw everything. I'm sorry. I think I'm just going to go for this because I also want to cover a lot of stuff today. So I'm just going to keep it there, I think. Hey, Chandra, how are you doing, sir? All right. So, okay, so I'm going to save this. I'm going to open the previous one and I'm just am I going to, should I start from scratch? No, I'm going to start from, okay, so I'm going to start and we will edit this together somehow properly. Okay, but how do I actually find the coordinates of this point here in regards to this coordinate system that we have here? How do I do that numerically? Well, we actually can take advantage of a very nice, of a very nice property of the dot product, which is that the dot product turns out to be the projection of one vector on top of another vector. Let me show you what that looks like. All right, let me load the other diagram. Okay, let's imagine we are zooming into the local coordinate system. We're just only looking at the coordinate system, at the local coordinate system, right? So we have this reference local coordinate system that is somewhere in three-dimensional space. And then we have the point that we want to find the coordinates in that reference frame. What we can do is we can create a vector that goes from the origin of that reference point to the reference point itself. Okay, so this is very easy to do because we know where this point is in world coordinates, and we also know where the origin of this coordinate of this reference system is in world coordinates. The next thing that we can do is we can project the vector, the position vector of this point in the local coordinate system, we can project it onto the x-axis of the local coordinate system. As we do that projection, we can measure in three-dimensional space how long that projection is, and then that will become the local x-coordinate of this point in this reference frame. Similarly, we can do the same operation for the y. We can project the position vector onto the y axis of the local coordinate system, measure that projection, and then that's the local y coordinate. And similarly, we can also do the same for the z direction. But now, how can we project a vector onto another vector, and how can we measure that distance? Well, it turns out that I think we have seen this in a previous gem, but we can take advantage of the dot product of two vectors, because it turns out that the dot product, one of the meanings that the dot product of two vectors has is that the dot product of one vector on top of another vector, so for example the dot product of vector A on top of vector B, turns out to be equal to the length of that projection tends all right, let me say this again. The length of the projection of one vector on top of another, that length equals to the dot product of the two vectors divided by the length of the vector that we are projecting on. And it turns out that if the length of B equals 1, then it turns out that the length equals just the simple dot product of the two vectors. And typically what happens is that when we have a reference system, typically the axis, the vectors that we use to represent the x, the y, and the z directions, those vectors are typically unitized, because that's what most reference systems, that's how most of them work. And actually, if they're not, if they're like 2 units long or 3 units long, it means that the system is actually scaled in one direction, and we would still get that effect of that scaling in the okay, I am writing on top of myself. So if we perform the dot product of the position vector times the one of the axis, we actually get directly the length of that projection on top of that axis, because we're going to be working on the assumption that the vector of the axis vector that we're going to be working on is a vector that is unitized. All right. So that's going to be very simple. What we're going to do in this gem then is going to be we're going to create a local frame. We're going to create a position vector from that frame into that point. We're going to project that vector on top of the 3 axes, and that's how we're going to find the 3 coordinates of that point in regards to that local coordinate system. You want to take a look at how that is done? It depends on the system that you're using. It depends on the framework that you're using. You will have to choose a form of representing this 3-dimensional coordinate system. In most computational environments, computational geometry environments, that would be typically represented as a 4x4 matrix with 3 vectors representing the x, y, z directions and another vector representing the position. We're going to be implementing this in Grasshopper with C#. So in Grasshopper incorporates a structure called the plane, and the plane is basically an object that also has 3 orthonormal vectors x, y, z, and it has a location, it has an origin, which is basically the same thing as a 4x4 matrix at the end of the day. So this is what we're going to be using in this exercise. So let's take a look at that and let's get hands-on. All right. Shall we do this then? So much talking and no doing. All right. So let's go back to here. So we're going to have a point, okay? Okay, we're going to make this point here. This point is going to go, I'm going to move it in the C direction, okay? And I'm going to bring it into Grasshopper. I'm going to set this one point here, and this point has these coordinates. All right, whatever. Actually, let me just create the point in the world. So construct point, and this is going to be, for example, whatever coordinates, x, y, z. Okay, and this is going to be whatever this coordinate. So let's say, for example, 6, 5, and 3. Okay, that's probably fine. And now I would like to create a plane that has some random orientation in 3-dimensional space. So how can we do that? I guess I could. How can we do that in an easy way? That is not. So let me say that. So we're just going to create another point. This is going to be somewhere here, somewhere here, somewhere here, maybe. And then a vector that is going to be pointing, I don't know. I wish we could create like a random plane or something like that. How are we going to do that so that it's easy and clean? Should I just create 3 points in space and create a plane between them? Have we created a gem for that? Create a plane out of 3 points? We should do that. I'm going to actually write that to my list. Plane from 3 points. Okay, and then yeah, let's just do that. It's probably going to be easier. And then I'm just going to put this up here. Okay. Okay, and then I'm I'm just going to create a point. Okay, so point, one point here, another point here, and the third point is going to be this one here. And I'm going to create a plane from 3 points. So that's going to be this one, and this one, for example. Okay. Yeah, why not? And then, I mean, if we're going to be doing this, why not just have a point that is also brought in from set one point, set this point here. So, okay, so we have this here. And then we have, this is the plane. Reference point. Oh my god, okay, deconstruct point here, and then x, y, x, y, and z. Okay. This sounds about right. So we have a point, we have the plane, and we want to find what are its coordinates. So here we're going to create the point and then local point. Okay. I think with this we can probably get started. And then here, maybe I want to make the plane size a little smaller. What if I do one? Yes. Okay. Okay, let's start. Let's start. So what I have created here is, first of all, I have drawn a 3D point in Rhino that I'm bringing into Grasshopper. And you can see that if I deconstruct this point, I can see that the world coordinates of this point are 0.8, 5.6, and 3.9, something like that, right? And what I've also done is in order to have some other local reference frame, what I have done is I have created a plane by just using 3 points that I have also generated in Rhino, right? I have brought them into Grasshopper and I have created a plane oriented with these 3 points. Therefore, taking the first point as the center, the second point as the direction of the main direction X, and the third point as the one that defines the containment on this plane. You can see that this plane has origin in 1.3, 6.7, 2.5, and the C vector, the normal, is pointing in this direction. So I have this situation. I know where this point is in world coordinates, and what I'm trying to do is that I'm trying to find what the coordinates of this point would be in this local reference frame that I have here. All right. I can see visually that X is going to be large, Y is going to be probably very short, and C is going to be also fairly large. Okay, just a visual estimation. And then what I have done is I have placed a C# script component and I have created an input called the point that I want to check, another input that is the plane that I also want to, that I use as the local reference frame. And what I will generate with this component is a local point, a point in the local coordinates of this plane. Or what I could do is I could just spit out the X, Y, Z coordinates of this. Actually, let me just do that. We're going to spit out the X, the lowercase x, the lowercase y, and the lowercase c of that point in that reference frame. We need to remember to properly type all the inputs. So I'm going to right click here and I want to make sure that this is of the type point3D, and I want to make sure that the plane is also of the type plane, whatever that is here. All right. And then I'm going to put this in here. I'm going to put this in here. And I'm probably now ready to start doing some calculations. Okay? And you know me already. What I would like to do is I would like to create some function here that I can reuse in other components. And actually, I will reuse this function in a gem that I want to record right after this one. Where what I would like to do is I would create a function that gives me the local coordinates of a point in some other reference frame. So what that means is that that function is going to take as input a point and a plane. So for example, let me call that function local coordinates. And that function is going to take as an input a point 3D called PT. And it's going to take a plane called the coordinate system, for example. All right. And then the return type of this function, what I want to get to know is the XYZ coordinates. However, we know that functions can only return one thing. Well, they can actually return several things if I do refs or if I do outs, but just for the sake of easiness, probably what I want to do is I want to return something that can encapsulate the XYZ properties of these points this point that I'm going to calculate. So probably what I want to do is I want to return either a point 3D object or a vector 3D object, because there I will be able to pack in those X, Y, and Z coordinates that I'm going to calculate. Okay. So, and then here in my code, what I would like to do is I would like to say, well, I'm going to create a point 3D object called P, which is going to be the result of calculating these local coordinates from the point that has been given to me in the component and the plane that is given to me as the component. And then here on X, I would like to return P dot the X coordinate. I would like to return here the Y coordinate of that point. And for Z, I would like to spit out the Z coordinate of that point. All right. And if I run this code, it's going to fail because right now my function, this one should be returning something. And because I haven't fulfilled that function yet. So what I'm going to do is I'm going to say returns the point in local returns the point PT in local coordinates of the plane of the coordinate system parameter. All right. All right, cool. Now, what is the next thing that I would like to do? What I would like to do, remember, is I have the plane, okay? And I have the plane, and what I want to do is, let me clean up a little bit of the mess here. Well, I have the plane, I have the point, so what I need to do, first of all, is I need to create the vector, the position vector, and I need to project that position vector to each one of the three local coordinates, local axes of the plane. So the first thing that I'm going to do is I'm going to create the position vector. So that's going to be vector 3D. It's going to be position vector. It's going to be a vector that goes from the origin of the plane. It goes from the origin of the plane to the point that I want to go. So the way I can do that is by saying, well, I can just take the point, and from that point, I can subtract the origin of the coordinate system. So that's going to be coordinate system. This name is very long. I'm just going to do CS here. Okay, coordinate system dot origin. By doing the subtraction of the target point minus the origin point, what I do is I create this one vector that goes from the origin to the target. All right. Now, what I can do is I want to find the length. I want to find the projection of this vector on each one of the axes of the plane. So remember what we just described here. If I do the dot product of that vector with the x-axis, because the x-axis is in unit vector, I will directly get the length of that projection as I have it here in this formula. Because this, for the axis, this b, for each one of the x and the y and the z-axis is unit. So therefore, the length of the projection L is just the dot product. All right. So what I can do is I can say, I'm going to create a variable of a double, and that's going to be projection on the x direction. And that projection is going to be the position vector times the x-axis of the plane. So cs dot x-axis. Remember that in Rhino Common, the multiplication symbol stands for the dot product. We could also do this manually, and actually I think I have a function somewhere that we can use for the dot product, but we can also shorthand it. D in Rhino Common means dot product. Okay, and so we can shorthand it with that. Otherwise, if you don't have this in whichever system you're working, if you don't have the multiplication operation between vectors as the dot product, you can compute this yourself. I have a gem somewhere somewhere. Actually, you know what? Let me go find that out. I'll be right back. Hold on 1 second. I don't remember where I have that, but I don't remember where I have that. Does anyone remember when did we do the dot product? When did we write an implementation of the dot product? Douglas Pecker, point to line, distance, this one in Geometry Jam number 2. Okay, yes, Geometry Jam number 2. Parametric cam, Geometry Jam, point to line, distance. You see the dot product, distance, the dot product. Dot product of one vector with another vector. So I'm going to write this here, dot product, and from Geometry Jam number 2. Okay, and I was doing this, right? Okay. And there we go. So from in Geometry Gem 2, when we discussed the distance from one point to a line, we also discussed all the properties of the dot product. That's where we discussed them before. So if you wanna know more about all this stuff that I have around me, just go to Geometry Gem number 2. Okay. So here we have the dot product. So I could also just say dot product and then one of these and the other one. Okay. Same thing. So I'm going to do that for both the x, the y, and the z. So that's going to be position vector, and this is going to be the y-axis, and this is going to be the z-axis. And then the only thing that I need to do is I just need to return a point with those 3 coordinates. So I can just return a new point 3D with projection x, projection y, and projection z. All right, and I think this should work, right? Let's take a look at that. So I'm going to do this here, okay? And as we estimated, x is large, y is not very large, and z is also kind of large. I wonder if there's any grasshopper plane coordinates. What are the plane coordinates? I wonder if we can double check this. So input point, so that would be this one. S is going to be the local coordinate system. And then here we would have x, y, and z. All right. This looks good to me. So the grasshopper, oops, actually my head is in the way. The grasshopper component, both our implementation and the grasshopper component, they both yield the same result. So we're either both right or both wrong. But at least this is looking good so far. Okay. So with that, this is what I would like to do for this gem. What we have discussed, what we have proved is how to take a point that is in world coordinate system and how to project it into a local coordinate system, or another way, how to find what the XYZ coordinates according to a local coordinate system would be for that point. Okay, again, this is a super useful operation when you want to do transformations between planes, or when you're doing like computer vision, and like you have to work with different reference systems. This is a very common operation to do. Okay, now what I would probably like to do in my next gem is show you how, having a point in a local coordinate system, how can I generate that same point in a different coordinate system with the same reference. That's typically an operation that is called a change of basis, and I'm just going to record a geometry gem right now to show you how to do that. So follow me up on the next video, and if you found this useful, if you like what you learned today, just feel free to subscribe, notifications, hit I like, etc., etc. Tell your friends, well, you know, all those things that we do in modern YouTube days. Thanks a lot, and have a good one. All right, and now I need to record the introduction. Okay, so that's going to be local coordinates. That's going to be local coordinates, and we're going to call this again local coordinates. And then introduction. What am I going to say for the introduction? It's going to be a short one. Okay. Hi, and welcome to another geometry gem. In this gem, what we're going to do is we're going to find what the coordinates of a point that we know where it is in world coordinates. We're going to find what the coordinates of that point could be in some other local coordinate system that is not the world. So, for example, in this view, what you can see is that I have this point here, and I know that this point is in this XYZ world coordinates. But what I would like to know is for this other coordinate system that I have somewhere in three-dimensional space with some random location and some random position, and some random orientation, I would like to know what the coordinates of this point are in reference to this local coordinate system. You can see that the coordinate system is much closer, so they're going to be smaller. So what we've done here is we have written an algorithm to figure out that translation between the world coordinate systems of this point, the world coordinates of this point, and the local coordinates of this point in this other plane. This is an interesting application because we're going to see one of the advantages of using the dot product for projecting vectors on top of each other, which is going to give us a really interesting result. And it's also really good for operations of changes of basis. So understanding how to move from one coordinate system to another, and which will also be very useful for operations such as translations or reorientations from one coordinate system to another local coordinate system, which we will expand further in the next geometry gem after this one. So let me explain to you before the concept behind what we're going to be doing, and then I will get into the implementation of how we did this exercise. Let's draw some sketches, shall we? Alrighty. Okay. How was that? Was that clear? Good? Bad? Did you get it? Not get it? Should I go over anything before I now show you how to go from one coordinate system to another coordinate system? How to do a change of basis? Should we do that? All right. I'm going to go get some water. I'll be right back. If you have any questions, please post them in the chat. Otherwise, we're going to now write another gem about going from this plane and then taking it to another plane, which is going to be like super, super easy now that we know how to do this. All right. I'll be right back. Give me a minute. My throat is very, very thirsty. I'll be right back. All right. Alrighty, so let's go back to the drawing board. What are we going to do now? We are going to... I'm going to go back to the previous one. That was this one. And I'm probably going to draw on this one. Let's... Yes. And then here, what I would like to do is I would like to explain the problem that now we have. So now we're here. And now I want, if I have another coordinate system, so many coordinate systems today, huh? I'm going to make you all very dizzy. We have another coordinate system here. And we have another coordinate system here. And we have another with another vector here. We may want to find where that point is in this coordinate system, right? So what we can do is we can say, I just multiply. What we can do is I can say, okay, I'm going to take this point and I'm going to multiply. I'm going to multiply it. Are you here this much? Oh yeah, you're seeing me, right? Here, I'm going to also multiply it here. And then I'm also going to multiply this here. Oops, nope, that was black. And then here, and then what I can do then is I can say, all right, so then this is, and this is, and this is, and this is where the point would be. My second point. All right, and then I can have that ready here, and then I probably want to we are not seeing the background. What you draw? What do you mean one way? You're not seeing the background. Which background? All right. Actually, I did not. Those three vectors are not orthonormal. They're not following the right-hand rule the way I drew them. Well, if you look at that going that way, I guess they are. So yeah, so I'm going to make this super, super lean. So I'm not sure what you mean one way about seeing the background of what I draw. If you can specify, please. All right, so this is the second geometry gem today, which is going to be a change of bases. So actually, this diagram is also pretty bad now that I have it there. Okay. Okay. So we're going to do change of bases. Okay. So let's discuss the problem. As we said, we're going to be building upon what we've learned in the previous gem, where what we were able to do was to find for a point that was defined in world coordinates, what we were able to do was to find what the local coordinates of this point for a particular reference system like this one could be, right? And this is going to be the basis of what we want to do in this gem, because in this gem, what we want to do is we want to say, well, we have a point defined in some kind of local coordinate system, all right? And then we have now some other coordinate system that is somewhere else. And what we want is we want to create a new point in that coordinate system that has the same relation from the old point to the old coordinate system. So whatever the local coordinate system, the local coordinates of that point in the first system are, I want those local coordinates to be the same for the new point that I'm going to be creating in that new reference system. And ultimately, because I always need to work in world coordinates, I will need to be able to find what are the world coordinates of that second point. The idea is the following. Imagine I have this point and I have been able to find, I know it's x, y, z in world coordinates. I know what the local coordinates of this point are. And then I have some other coordinate system that is somewhere else in the world. What I would want to do is I would want to be able to take the x, y, z local coordinates and apply them in this system so that I would end up with a point that maintains the same relation with this coordinate system than this point maintains with this coordinate system. And then what we're going to do is going to be very simple. What we're going to do is we're going to take the origin of this point, the origin of this coordinate system, and then we're going to add to that origin, we're going to add a position vector that is going to be pointing this way, and it's going to be the result of the x-axis multiplied by the x coordinate times the y-axis multiplied by the y coordinate and the z-axis multiplied by how many units in the z-axis this point should be. Let me actually draw a diagram where we see that more clearly. All right, so let's say we have here coordinate system, x-axis, y-axis, and z-axis, all right? And then we know that we want to point x with x, y, and z coordinates, right? According to this. So what we can do is we can say, okay, so then, what we can do is we can create a vector with these coordinates. So we can create a vector. That vector can be anywhere. And then if what we do is we just take. No, that's not what I want to say. What I want to say here is if we now multiply this by x, all right? And if we now multiply this by y times, we scale it. And then we multiply this by z, then we end up having something that looks like this. We end up having something like that, and we end up with a position vector that goes from here to here. Okay? And therefore, once we have that, if we take the, let me go here, and I'm going to name this position vector V. All right? And now if we do that, then now if we take origin and we add the vector, we end up having P, and O. And with P being equal to, actually I can do that in the previous, I can with P, where is P? With P being equal to 0.0 plus vector B. Is that correct? Hey, no, good afternoon. How are you doing, sir? Good to see you. Are you done recording for today? Are you recording today? Okay. All right. So, okay. Oh no! Wait. I have to. Yeah. Okay. All right. All right. And then we're going to delete this. Okay. So let's zoom in the new coordinate system that we have, and let's zoom into the problem of we know the XYZ local coordinates of the point that we want to generate in this coordinate system. Okay, because now we need to figure out how to do that. With vector algebra, it turns out that it's also very easy to do with vector transformation, because for example, if we know that the point that we want to get is in x units along the x-axis, y units along the y-axis, and z units along the z-axis, so those three numbers that we have there, what we can do is we can just multiply each one of the three axes, so we can scale it x, y, and z. We can scale the three axes of the reference frame. And then with those three vectors, if we add them together, what we obtain is a position vector that looks like this. What we obtain is a position vector that looks like this. It's a vector that contains, that is the addition of the three vectors. It's a vector that has the three coordinates x, y, z of those Cartesian systems. And then after that, it's very easy to do. In order to find the coordinates of point P, the only thing that we need to do is take the coordinates of the point O, the origin of this reference system, and just add the vector that we have found in three-dimensional space with this coordinate system. So it's a very simple rule. P, the point that we want to find, is going to be equal to the origin moved by that position vector. So let's get busy. Should we see how to make that with code? All right. Are we ready for this? I'm going to save this. Yep. And let's go back to here. we have this point. I'm actually going to bring this point a little closer. I'm going to bring it here. Okay, somewhere here. All right. And then what are we going to do? I'm going to save local coordinates. I'm going to change of basis. For example, I'm going to save this as change of basis. I have the point, I have a plane, and then I'm just going to create 3 other points that I'm going to use as this one here, and then this one here. So I'm going to, so this is going to be this one, this is going to be this one here, and this one is going to be this one here. Okay. Alrighty. Turns out they have like a very similar inclination. That's probably not great. So what if I do that? Okay, so maybe that doesn't look terrible. Okay. Okay. All right. So, all right. All right. So let's get started. We're going to be implementing this in C# for Grasshopper, which is a procedural modeling environment that is a plugin for Rhino. But this process that we're going to follow applies to any framework that you can think of that has some kind of geometry kernel. Grasshopper happens to have plane objects, and plane objects being this structure that contains 3 orthonormal unit vectors, x, y, z, representing the orientation, and a point that represents the origin of that plane. We can think of this, if you're more into 4x4 matrices, you can think of that as the 3 vectors as the rotational part of the 4x4 matrix, and the origin as the translation part of the rotation matrix. It's basically the same concept. And I'm going to be building upon the work that I have done in my previous gem, where we discussed how to, given a point and given a reference system, how to find the local XYZ coordinates of that point for that coordinate system or for that plane. So what I'm going to do is, what I have done is I have created a second plane, also from 3 points using functionality that is available in Grasshopper. And then what I'm going to do is I'm going to extend this exercise so that I can now generate a new point that is going to be at the same local coordinates at this point as this point in this plane for the new coordinate system. And I would like to find what the world coordinates of that point are in this new reference frame. So what I'm going to do for that here is I'm going to rename the plane. So I'm going to call it source P, and then I'm going to create a new input in the component that is going to be target plane or source. I'm going to call this source coordinate system, and I'm going to call this target coordinate system. I kind of like that definition a little better. I'm going to plug this in here, and I'm going to remember that I need to right click and set that the type of this input is of the type plane, which is how in Grasshopper coordinate systems, frames, or 4x4 matrices are defined. Okay. Now I'm going to delete the outputs, and what I want for output is what I want to do is the the new point, the point that is going to be, or the point in new C coordinate system, for example. Or no, I actually don't like reoriented point. I'm really bad. This happens to me all the time. I'm really bad with like coming up with names for things. Okay, and then as I double click, you can see that the code that we have is from the previous gem, where we created a function called local coordinates that we use to find from a point in world coordinates and a coordinate system, find a point with the coordinates in that local coordinate system. What I would like to do now is I would like to create another function that is given a point in world coordinates, given a point in local coordinates, find what that point in world coordinates would be for a particular plane. So the process that I have described before. So what I'm going to do is I'm going to create a function called point on plane. All right, for example, and I'm going to say that is going to have the x coordinate, the y coordinate, and the z coordinate. And I'm going to say something like this. Okay. So I'm going to create a function that, given a plane and given x, y, z coordinates, it generates a point that is on the x, y's. I'm going to call it local point on plane. All right. And the return type of this should be a point3D object, because what I want is that object. Okay. So this is going to be very easy now. As I described before in my drawing, what I will need to do is I need to create a vector 3D object that is going to be called the position vector, which is going to be equal to the x direction of the plane scaled by x. So that's going to be x times cs dot x-axis, so the x-axis vector of the plane that I have multiplied scale by those x coordinates, plus y times cs dot y-axis plus z times cx dot z-axis. All right. So remember, according to my diagram, what I have just done is I have created a vector that is a combination of the x-axis scaled by x plus the y-axis scaled by y plus the z-axis scaled by z. I have my position vector now. So what I can do now is, in order to find that point, so in order to find the point 3D pt or p, whatever I want, what I can do is I can say I want that point p to be the origin of the plane plus this position vector that I have defined. So that is going to be very easy again. In Rhino, I can use the multiplication operator I can use the addition operator to add points and vectors. So in Rhino, what I can do is I can say this is going to be equal to cs dot the origin, so the origin of the plane, plus that position vector. All right. If you don't have that possibility on your framework and the framework that you're working with, an alternative could be to just say point 3D P is going to be equal to a new point object, all right, which has cs.origin plus the x coordinate of, origin dot x plus the position x, then the second coordinate of this point is going to be the y coordinate of the origin plus the y coordinate of the position vector, and then cs dot origin, the c location of the origin plus the c coordinate of the position vector. All right, these two operations are actually the exact same thing. So I'm going to, this will be manually, and this is going to be using Rhino common operators. Okay, so they're both equivalent. And now my function should just return that point P. Okay. So what I could do now is very simply, I can just say, well, I have point P is the local coordinate of the point that I have been given in the source coordinate system. All right. And now what I can do is I can say point 3D new P is going to be equal to a local point on plane with P dot with on target coordinate system, and then P dot X, P dot Y, P dot Z. And then the output of this reoriented point should be equal to that new P that I just created. Let's see if this works. Oh, is this working? Let me see. So it looks like this point is like on the X and Y, is like a little over X and Y, and here it is on the other direction, because here you see that the two directions are flipped. Okay, so this is X and Y. Let's do an exercise. Let's see if we use vanilla Grasshopper to find the coordinates of this point in this coordinate system. We should get something like something like this. Okay, but if we do it on the other one, we should get the exact same thing, which we are not getting. Oh, sorry, the other point. Oh no, because yeah, because it's sorry, this is not the check really. So this should be the reoriented one. Exactly, the reoriented one should have the same coordinates as this one. All right, exactly, yes. Okay, this is what happens when you rush things. You see, because this point, the original point, should have the coordinates on this plane, these ones, and this new point that I just created, this one here, should have the same local coordinates on this plane. So that's what was happening here. All right. Now, why are we doing this? Why is this useful? Well, this has been very useful because now, if I move this point, you can see that whatever transformation I do on this point, this other point is going to keep the same relative location to that original point. But let me actually do a quick exercise on like why this could be cool. Let me show you an example of a cool application of this. Hold on there. So let me create a random surface, sort of. I'm going to create, for example, all right, and then I'm going to lock this. Just going to move this here. I'm going to do X-ray, and then I'm going to bring this surface. I'm going to bring this surface inside. So let's set one surface, and then I'm going to subdivide this surface into perpendicular frames, for example, and then I'm going to fit these frames to the target. Can I flip the frame? Yes, there you go. Okay, and then I'm going to move this somewhere. There you go. No, I don't want this. Yes, exactly. Wait, have this. Okay, fine, whatever. Okay. All right, so check this out. Really quick exercise. I have created a loft surface in three-dimensional space. It's an Earth surface, so it has UV directions in both its main directions. I have brought that into Grasshopper, and then what I have done is I have divided this surface into a grid of UV tangent planes. So each one of the planes is tangent to the surface, okay, and it's maintaining its relative orientation. So now what I've done is I have plugged, instead of using the original target plane that I used in the exercise, what I have done is I have plugged each one of all these planes into the target translation. So basically what I'm doing now is that for each one of these planes, I am creating a new point that has the same local coordinates. Then these two relationships, it has them here so each one of these points is holding a relation to its reference plane, the same one as we can see here between this point and the source target plane. So why is this interesting? Well, it's interesting because it can give us a way of offsetting the surface or making operations with the surface or with elements of the surface. Or if, for example, if I had a mesh object, let me actually do that with a mesh object. Hold on. Okay, so let's go back here. So now let me create a mesh, for example, a boring mesh. Where do we have meshes here? Here. Oh, what the hell? View, display, preview meshes. Yeah, this is difficult to see. I want something that we can. I wonder if we have. So this is a mesh box. Deconstruct mesh, and then construct mesh. We have all the vertices, and then we have, for example, then here as X, we have Y, and we have C. Oh no, this is the mount. Oh, and this is the base. Oh, okay. Oh, lame. All right, let me just do this manually. Sorry. I'm just going to create a cylinder, a mesh, offset mesh, a cylinder here. And that cylinder is going to be somewhere here, for example. All right, and I'm going to bring this into here, set one mesh. All right, so I'm going to deconstruct this mesh. I'm going to deconstruct the mesh here, so I get all the vertices, and now what I can do is I can just pass all these vertices here. And then I can just hide this. I can just, okay, and then I can reconstruct those with the same point information. Okay. So with a mesh, it looks something like this. I have created a simple cylinder mesh in Rhino. I have brought it into Grasshopper, and I have deconstructed the mesh into vertices, faces, colors, etc. Everything that is contained in a mesh. But at the end of the day, think about meshes as just point clouds that are joined with triangles. And because each one of the points, each one of the vertices of a mesh is a point, what I can do is I can feed all the points of the mesh to this tool that I have created to take the points from this coordinate system into a different coordinate system, and the result is that what I get is basically that cylinder translated from this coordinate system to this other coordinate system. So if I move it around, you can see that the relative position between the two elements is maintained the same. You can see that the cylinder is now kind of intersecting the plane, right? And you see how the cylinder is also like holding the plane here in three-dimensional space. And finally, because in Grasshopper I have the connectivity of the faces, I can reconstruct that mesh in 3D space by using the translated vertices, but using the same connectivity of the faces. All right. So therefore, I have now my translated cylinder from one local coordinate system to the other local coordinate system. Okay. I think this is pretty cool and pretty neat. This operation can also be done, change of basis can also be done with matrices. It can also be done with special transformations in 4x4 matrices. But I wanted to break down first like the fundamentals of this process, and maybe at some point in a future geometry jam we can take a look at how change of basis actually looks from a more with a matrix operation. Okay. I think this is what I want to stop here. Thank you very much for sticking around. I hope this was fun and useful for you. I think I might be using this technique of finding XYZ locations of a point in a local reference system very often in my future geometry jams, like for example the one that I'm thinking of recording next, which is going to be just stay tuned and you will see what that happens, what the geometry jam is. Thanks a lot for being here. If you like what you saw, please subscribe, hit the like button, notifications, all the good stuff. Show your love, spread the word, tell your friends, and all those things. Okay. And in the meantime, I'll see you on the next video. Thanks a lot. Oh, all right. Okay. Change of basis is done. Oh, the introduction. I have the introduction. Wait. The introduction. Uh-huh. Okay. And let me hide this here. All right. Okay, introduction. Hi, and welcome to this geometry jam where I'm going to expand on my previous geometry jam where we learned how to find the local coordinates of a point in a local coordinate system, not the world coordinate system. And now what we're going to do in this geometry jam is to figure out how to now recreate that local point from a reference system into a new local coordinate system. This operation is typically referred to as change of basis. So what you have here, for example, is you can see that I have this point in reference to this plane, and you can see that this point, now that I have created with this algorithm, is basically maintaining the same x, y, z local relationship with this plane than the original one had with this other plane. Think of planes as coordinate systems, is the same. And the idea is that this operation is really good because it allows us to do basically reorientation of geometry from one local coordinate system to another local coordinate system. Like for example, I have in this exercise where I have created a surface, and in this surface I have found a lot of tangent planes. And what I have done here is that I can use my algorithm to replicate the relationship of this point to this target plane, so this source plane, with any of those planes here. So I can now create like a collection of points with that same orientation here on top of this surface. Similarly, what I can do is I can, for example, apply this application. I can apply this to any geometry. So for example, if I have a mesh that has a bunch of vertices and faces connecting them, basically I can extract all those vertices because a mesh is just a collection of points that are connected with faces. And if I translate and reorient each one of those vertices, then I can end up with a cylinder that has the same relation to that coordinate system than the previous one. So effectively, having reoriented this geometry from one local coordinate system to another coordinate system. This exercise is building on top of my previous gem. So if you haven't checked that out, you probably want to give it a look before we go into getting hands-on. And before we go into getting hands-on, let me please explain how we're going to be doing this by explaining it conceptually with a couple of diagrams. Let's take a look at that. All right. Okay. How's everyone doing? I'm a little tired. I think we're gonna call it a day here. Oh, I am open to some questions or some conversation if anybody wishes. Otherwise, I'm ready to start the weekend. I don't know what you think, but I'm very ready to start the weekend. Any questions? Any comments? Mm. All right. Well, if there isn't anything going on, I think I'm going to start cooking dinner, and I'm going to go to bed early. Woohoo! All right, wonderful. So thank you, everyone. Thanks for sticking around and sharing your Saturday with me. It's a pleasure, as usual. And I think next time we meet, we're probably going to get into into classes and objects and finish the learning C# list. Okay, I would like to do that. All right, thanks everyone. Good to see you. And until next week or next weekend or however, whenever that happens. Bye bye. Thank you.